Okay, so today we'll be talking about how to solve the two equations that we have seen, the econometrics equation and the calculus equation, how to solve them numerically. So that will be our topics today. Okay, so let's look into the econometrics equation first. So here the equation that we are trying to solve is XA plus A transpose X equals C. All right. What is the first thing that comes in your mind? How do you solve this? How do you go about solving this numerically? Well, we have to think that the natural thing to do is to transform the matrix A or A transpose to a convenient form, right? To a form which is much simpler than the matrix A itself. Some convenient canonical form, right? And then solve the problem using the structure of that canonical form. And finally, recover the solution of the original problem from the solution of the transform problem or reduced problem. So what sort of convenient canonical form we are talking about?
Real Sura from Eisenbach's.
Well, the simplest form it will be diagonal matrix. But a matrix cannot always be diagonalized. Even it can be diagonalized. The transforming matrix can be very highly ill-conditioned. Okay, so that's not a good way to do it. What is the next thing? So next convenient canonical form will be transform the matrix A to controller canonical form, which is the convenient form of the matrix. and we know the problems there, right? So what is the next thing? The Heisenberg form or the real Schur form, right? Now, if you transform the matrix A or A transpose to a real to a Heisenberg matrix, then we have to solve some Heisenberg systems of equations, right? To get to compute the idea will be to compute the matrix A column by column. On the other hand, if we can transform the matrix A or a transpose to a triangular matrix or quasi-triangular matrix like real Schur form, then the computation will be a lot easier, right? So let's try to do that to see whether we can how it goes. So the first thing is that we have to transform the matrix A or A transpose to a real Schur matrix. Now, since we are solving here not AX plus A transpose, AX plus X A transpose equal to C, we are solving the other way. We are solving XA plus A transpose equal to C. So let's try to transform the matrix A transpose to real Schur. Okay. That means let's compute this. Let's transform the matrix A transpose to real Schur form. U transpose A transpose U equal to R, right? So if you do that, let's see how this equation gets transformed. So we have X A. Now, how do I insert U here to get the things going? What do we do? Well, U transpose A transpose U equal to R, right? What it means. So if you multiply both sides by U, what you get? If you multiply by U to the left and U transpose to the right, what you get?
A equal to
You get
U transpose
U transpose A transpose. Okay. And so what this means A transpose will be U R
R U
U,
transpose.
right? Or we can just let's do the following. So what we can do, we have XA, so we can do U. Oh, I'm sorry, I need A, not A transpose. So here, if you multiply both sides by multiply the left hand side by U and the right hand side by U transpose, what do you get?
R A transpose.
You get A transpose equals U R U transpose, right? Right? Because U transpose U equals identity. That means A equals U R transpose. So let's make the
U transpose R transpose U.
Hmm?
A equal to U transpose R transpose U.
You take the transpose of this, you take the transpose, and transpose goes the other way, right?
Yes.
So it's U R transpose U transpose, right? So we have X A U R transpose U transpose. plus A transpose equal to U. A transpose U, U R U transpose X. C. Okay. Now do the following. Multiply both sides by U transpose. Okay, to the left. And so if you multiply both sides by U transpose, so U transpose X U R transpose plus R U transpose X. Right? Right? Now what I do? Well, I bring here U transpose. So I can write this as U transpose X U. Right? And then I say U transpose U R transpose. Plus. So what I'm trying to do, I'm inserting U here. So so U transpose U is identity. So this U will be there, right? And then okay, let's do the following. Let's say U transpose X U. U transpose X U, we got to say call this Y. Y. Okay. And R transpose U transpose. R transpose U transpose. Plus R U transpose R Y. Right? All I'm calling that U transpose X equal to Y. Right? Okay. And now what I do, I multiply by U transpose to the right. So I have Y R transpose U transpose identity. So we have R Y U transpose C U transpose. Right.
Second, I will
So I'm multiplying by U transpose to the right. So Y R transpose U transpose identity R Y
U transpose. U transpose.
R transpose and then U transpose. It's like
Y
R transpose and then U transpose.
or Y R transpose U transpose. Okay, I made a mistake. Good.
Is
And then R Y for U transpose.
RY U transpose.
Okay, I'm saying that
It's like it will be RY and
U transpose X C equal to Y, right? So this is Y R transpose U transpose, right? Plus R Y equal to U transpose C.
Y, then we have to multiply U transpose, it will be U transpose. RY U transpose. RY U transpose.
No, I say U transpose X equal to Y.
U
Right?
transpose is equal to Y.
Yeah.
Is it
No, I'm sorry. U transpose X equal to Y.
Yes.
Okay, so this is Y R transpose U transpose. All Y C you are right, right? Okay. So I need to I need to multiply by u. I need to multiply by u on both sides. So I have u transpose x u r transpose u transpose u plus r u transpose x u equal to u transpose c. Okay. Now I'm there. So this is my y, and this is my r transpose. This is identity, and this is ry equal to say or c. Right? So that's what I have to take. See. So by reducing the A transpose to real suit form, then the equation xa plus c transpose x equal to c reduced to y r transpose plus ry equal to c c hat, where c hat I call it c prime here, is c hat. Yeah. So c hat, but c hat is nothing but u transpose c, right? So from xa plus a transpose x equal to c, now that equation reduces to y r transpose plus ry equal to c. Okay. So now the thing is that I can compute the matrix Y column by column by taking advantage of the structure of the matrix R, because R is in a very simple. R has the form, it's a quasi-triangular matrix, right? By taking advantage of the structure of the matrix R, we can compute now Y column by column. That's good. If, for example, if R were a triangular matrix, that means there is no 2 by 2 blocks on the diagonal. Just a triangular matrix. Suppose it is triangular matrix. Then each y1 will be computed column by column. That's it. Okay. For example, take an example. Suppose for the simple case. So this is what we are trying to solve. Y r transpose plus r y equal to c prime. Okay. Okay. Suppose R is a triangular matrix. Okay, upper triangular matrix. So I have, and suppose let's take n equal to 3. Or actually I have here equal to 3. Suppose a triangular matrix, what happens? Yeah. Suppose R is an upper triangular matrix. So in that case, that y1, y2 through yn are the n columns of the matrix Y, right? Then you can see the y r transpose plus ry equals c hat. Let's call the entries. Let's call the columns of the matrix C hat as C1, C2 up to Cn. So if you do that, then you get this system equals to solve. That means it's a solve, because it's a triangular system. You're solving by back substitution. That means you are computing the columns of y from y1 up to y. So first you compute yn, and then once the yn is computed, then you compute yn minus 1, and so on and so forth. So at the last equation you compute y. And each time you are solving a triangular system, because R is a triangular matrix. This is the simplest case. When R is a triangular matrix, that means that all the diagonal blocks of the matrix, of the real suit matrix, are scalars. There are no 2 by 2 block matrices there. Okay? You understand what I did, right? It's simple. Any doubt here? Take n equal to 3, then you will understand. Right? Okay. Now this is the simplest case. So suppose that we now have some 2 by 2 blocks on the diagonal. Then how do I handle that case? Well, you can, why don't you think what you want to do? Instead of R being a triangular matrix, now R will be a matrix with some 2 by 2 bumps on the diagonal. So how to handle that case? Again, the idea would be to compute the matrix Y column by column. Like how to do that then? Let's take a simple example here. Suppose your R matrix looks like this. That means here R21 is different from 0. So this is in real Schur form, right? There's one 2 by 2 block and one scalar, right? And this is 3 by 3 n equal to 3. So there are 3 columns of the matrix Y, right? So if you just plug in there Y R transpose equal to R Y equal to C prime and C hat, then you can easily see that Y3 can be computed by solving, Y3 can be computed by solving this triangular system, right? And once Y3 is computed, then you can compute Y1, Y2 simultaneously, okay? Because then there is a 2 by 2 block case. So in that case, your Y1, Y2 will be like this. You can, this is simple mathematics. You can do it on your paper and verify that. That will happen. Okay. So here you will compute Y1, Y2 simultaneously by solving this simple system. So what will happen? This will reduce to a 2 by 2 linear systems involving Y1 and Y2. That's it. So do you get an idea, overall idea? In the general case, what we'll do? In the general case, for every subdiagonal which is not equal to 0, that is 2 by 2 block case, right? Those 2 by 2 block, for the 2 by 2 block case, the corresponding columns of the matrix Y will be computed by solving a 2 by 2 linear system. And when the subdiagonal element equal to 0, that means we have a scalar case. The corresponding column of the matrix Y is solving just by solving triangular system. That's it. That's the whole thing. So let's look in the general case now. Yeah, here is the case where, as I said, one of the subdiagonal elements Rk k minus 1 equals 0. In that case, we have that the corresponding block is a number. It's not a 2 by 2 matrix; it's a number, right? So in that case, the corresponding column of the matrix Y, Yk, will be computed by this lesson. This is simple mathematics. You can just work it out. And in the case where Rk minus 1 equal different from 0, that means we have a 2 by 2 block now. So corresponding this 2 by 2 block, there are two columns of Y, Yk and Yk minus 1, like k minus 1. And that has to be computed by solving a 2 by 2 linear system. You understand? So whole thing is so simple. Once you transform the matrix A transpose to a real Schur. And this transformation is numerically stable. Okay. Of course, once the matrix Y is obtained by solving this equation, then you can immediately compute your matrix X from Y, right? Remember what is the relationship between X and Y? Y
U transpose X.
U transpose X,
U.
U transpose X U equal to Y, right? So multiply both sides by U and multiply left hand side by U, right hand side by
U transpose.
so you have X equal to U Y. That's it. And again, this matrix multiplication is stable because
It involves orthogonal transpose.
that's right, because we are involving one of the matrices, at least one of the matrices is not orthogonal matrix. And I said that matrix multiplication in general can be an unstable process. But if one of the matrices happens to be an orthogonal matrix, then the process can be shown to be a stable process. So the whole thing is stable and simple.
Sir, if there are n columns in Y, then we have to solve first nth
Or
equation.
you have to look into the structure of the matrix R, right?
If it is block diagonal form,
Yeah.
then if solving for nth equation, then rest all equations will be solved simultaneously.
Sorry.
Block by block.
Sir, as you have said about the third order case, and then we are solving for third equation also.
Yeah. We are in when n equal to 3, we have 3 columns to be solved.
Sir,
So one column that corresponds to the scalar entry, that is solved by solving a triangular system, upper triangular system. And other two are solved, other two, y1 and y2, are solved simultaneously by using a 2 by 2, by using a system of 2 by 2 linear equations. I'll give show you an example of it. So you need one thing, that the comment I made about the Lyapunov equation, Lyapunov stability. I mean, taking the stability of a linear system by using Lyapunov matrix equation is counterproductive. Because in order to solve the Lyapunov matrix equation in a numerically viable way, you need to transform the matrix A to a real suit form. And the real suit form of the matrix contains the eigenvalues anywhere, right? The scalar entries are the real eigenvalues, and the complex conjugate eigenvalues, each 2 by 2 block, the eigenvalue of each 2 by 2 block gives a pair of complex conjugate eigenvalues. That means essentially the real suit form contains all the eigenvalues. And this is the only numerically viable way to solve the Lyapunov matrix equation. So if you want to test the stability of a system by solving Lyapunov matrix equation, that is a counterproductive. There is no point of doing that. But Lyapunov matrix equation, as I say, as we all saw, that has tremendous applications in control theory. There are many control problems that need effective numerical solution of the Lyapunov matrix equation. Okay. So we have to know how to solve it numerically anyway. There is one theoretical comment that I make, that there is a classical theorem due to SAGY, S-A-G-Y. Because one might be thinking, why I'm transforming a matrix A to a quasi-triangular matrix? Real suit form is quasi-triangular matrix, right? Why not to a triangular matrix? What is the problem there? In theory, you can transform a matrix to a triangular matrix, upper triangular matrix, using even unitary transformation. Unitary means the complex case of orthogonal matrices. You can do that. So there is a classical theorem due to SAGY is called Su triangulation theorem. That says the given matrix A, there always exists an unitary matrix U such that this is a triangular matrix, upper triangular matrix. Now, why it is unitary matrix? Because this upper triangular matrix, this is a unitary matrix is the complex person of a real orthogonal matrices. Okay. So I mean this matrix T is a complex matrix. Why is it complex matrix? Because this matrix T contains the eigenvalues of the matrix A, and some of the eigenvalues can be complex. If they are, if one eigenvalue is complex, the other one would be complex conjugate. They will occur in pairs. That's why U has to be complex in this case. And this is unitary. That means it's a unitary similarity transformation, or a numerically stable transformation. But what is the problem then? Problem is that you cannot compute, you cannot construct this matrix U without knowing the eigenvalues. So again, it's a counterproductive. In order to construct the matrix U such that U transpose AU is an upper triangular matrix, you have to know the eigenvalues of the matrix, eigenvalues and the eigenvectors of this matrix. Actually, the U will have the eigenvectors. So, as far as computing the eigenvalues of matrix A, this theoretical result, this outstanding mathematical result, it does not serve any practical purpose. Just for you to know that this can be done. Quick TV on Facebook. I don't do Facebook. Any questions so far? So I'll in your tutorial session I'll ask you to do a problem using this T-by-T problem. So then you have to know how to do that. Okay, you will get a feeling. Okay, here is an example. Okay, so how do I get this real Schur form? Well, MATLAB function gives the real Schur form. It's called Schur. You know that function, right? You use that. What is the noise? Okay, so using the MATLAB function Schur applied to the matrix A transpose, we get the matrices U and R. U is unitary and U is orthogonal. R is real Schur form, right? So again, there is a 2x2 block here, and there is one single block of it's scalar. Okay, and this is how your C hat looks like. So now the same thing, since there is a 2x2 block and there is one scalar, so what should we do? Well, the scalar corresponds to the column Y3 of the matrix 1. So we compute that first. And once that is computed, it's a back substitution, remember that. Once that is computed, then Y1 and Y2 are computed simultaneously by solving a 2x2 linear system. So that's what is happening here. So you got Y3 here, look at the Y3. Okay. Y3 is solved by the triangular system. And then Y1 and Y2 are solved. You can, you'll try this thing in your tutorial, see how it goes. Maybe it will be too hard to do that because you need a computer to do that. We'll give a simple case. And once you have the Y, so you understand what I did, right? So Y is computed column by column. That you have to remember. Okay. So the column the column yk corresponding to rkk minus 1 equal to 0 is computed just by solving it an upper terminal system. Okay. And when rkk minus 1 equal to 0, then you need to solve the corresponding columns by solving a 2 by 2 linear system. Okay. 2 by 2 upper triangular linear system. Sorry. And this is your y. By the way, the MATLAB has a command to compute the suit form that we talked about, this complex suit form. This is called suit matrix because it was discovered by the mathematician Suit. So this is the complex suit triangulation, and MATLAB has a command to do that too. Okay. So if you use MATLAB command, then your life becomes very simple, because then you are dealing with a upper triangular matrix. No 2 by 2 blocks. You know, the 2 by 2 blocks, they are called in numerical linear algebra literature, they are called bumps, because they create problems, right? That's why they are bumps. So if you use that MATLAB suit command, that complex suit command, then you can see that matrix R is upper triangular, though it's complex, but it's upper triangular, right? In that case, you can compute the columns of the matrix Y, column by column, but you have to use complex arithmetic, because some of the numbers are complex here. So you have to use complex arithmetic. Okay, that is twice as expensive as using the real arithmetic. Okay. But this is I'm not asking you to do that in practice, but this can be done. That's why, to avoid complex arithmetic, we came up with that form called real suit form, where you don't have to use complex arithmetic. And of course, the complex triangular form cannot be achieved without knowing the eigenvalue and eigenvectors. So this is not practical. Okay. But if you say I don't care for the eigenvalues and eigenvectors, suppose I know them, can I use that the complex triangular matrix T to solve a Lyapunov equation? Yes, you can do that. That's what MATLAB has done. All you have to do, you have to use complex arithmetic. You know what I mean? Any question?
And sir, indirectly, we are saying inside that code it is calculating eigenvalues, or it is even impossible to do this transformation.
Yeah, without computationally you cannot do that without knowing eigenvalues and eigenvectors. If you look into some theorem, linear algebra book, okay, like matrix analysis by Horn and Johnson, there's an outstanding and linear algebra book. And in that book, you can see how the proof of the suit triangulation theorem is given. You can see that in the proof, actually in my numerical linear algebra book, there's a proof also. Sorry, I forgot that. In my numerical linear algebra book, there's a proof. But the proof will involve knowing the eigenvalues and eigenvector. There is no current now, otherwise I could have shown it from my numerical linear algebra book. Okay. You can solve? Yeah. So to go to my numerical linear algebra book. Oh, this is running in battery. Right? That's why. So why don't you open the door so that
Above one.
So
Yeah.
I can do chapter 8, chapter 9. there's so much thing to talk about eigenvalue problems.
So what is the eigenvalue?
Then go to 356, page 356.
And
Is it? Yeah.
enter.
Okay, I can find it now, but here I told you the other day about the ill conditioning or well conditioning of some practical problems, remember? And I said the Wilkinson, the famous American institution, he made a remark. He's the one actually who started the whole thing by coming up with that, by example of 20 by 20 matrix, remember?
Yes.
Which eigenvalues are very ill conditioned. A small change in the 20 other element made all the eigenvalue complex, and I mean made some of the eigenvalue complex. Then he said, look at this statement. Although we have made it clear that with regard to the use of Frobenius form is the generalization of the companion form, as dangerous in that it may well be catastrophically worse condition than the original matrix. We have found the program based on its use surprisingly satisfactory in general for matrices arising from damped mechanical or electrical systems. So most of the practical problems arising in mechanical or electrical systems, they are not ill conditioned. That's the good news. We don't have to worry too much about conditioning of the problem. Yeah, it is common for the corresponding characteristic polynomial to be well conditioned. Okay. When this is true, method based on the use of the explicit characteristic polynomial are both fast and accurate. Okay. So if the problem is known to be well conditioned, then the use of characteristic polynomial is not a bad idea. Okay, that's what he's saying. Okay, well, there's no electricity now, so let's have a little break for 5 minutes, yeah, and then come back. Okay. Okay. So there exists an immediate generalization of the Lyapunov matrix equation called the Sylvester matrix equation. And it has some applications to control also. We'll see some of the applications later. So it is of the form XA plus BX equal to C. Where the matrices A, B, and C are given to you, and you have to find the matrix X. In the Lyapunov matrix equation, you have to find the matrix X given the matrix A, so that XA plus A transpose X equal to C. Right? Here, three matrices are given to you, A, B, and C. You have to find X. Now, how do you solve such a matrix equation numerically, in a numerically viable way? Well, we can transform both A and B to real Schur form, right? And then try to compute the columns of the matrix Y the way we did. Okay. It will be a little more complicated than the Lyapunov matrix equation, but it can be done. But one thing you have to understand, that transforming a matrix A to real Schur form means finding the eigenvalues, and that is much more expensive. Or actually, it's not only expensive, but okay. So what is the relationship between Heisenberg form and the real Schur form of the matrix? Okay. The thing is that real Schur form of a matrix is obtained by means of QR iteration algorithm. Remember that? Okay. We have to perform the QR factorization several times. Okay. Now, as I said, that if you do it n times, n iterations, each iteration will cost about order n cube operations. And then if you do n iterations, it will be a really expensive algorithm. It will be, the complexity will be order n to the 4, right? In order to avoid this situation, what we normally do, first we transform the matrix A to a Heisenberg matrix. And then we apply the QR iteration algorithm on the Heisenberg matrix. What do we gain out by doing that?
N square.
Right. Then we are doing, because when you transform the matrix A to a Heisenberg matrix, the eigenvalues are all preserved. Okay. And then we are doing QR factorization on the matrix H itself. That transformation is done once for all. Then we are doing QR iteration on the matrix H, and that each of QR iteration in that case will require order n square operations instead of order n cube operation for a full matrix. Okay, so that means Heisenberg transformation is a process, is a pre-process of finding the real Schur form. You have to do the Heisenberg transformation anyway. So the question arises here: out of two matrices A and B, why don't you do the following? Now, remember, A and B, they may not have to be. They are not necessarily, or in general, they are not of the same size. So suppose B is of lower order than A. So the idea will be transform the matrix B to a Heisenberg form, and B to a real Schur form, and A to Heisenberg form. Okay. and then try to reduce this equation to another equation. Solve that equation by taking advantage of the structure of the Heisenberg and real source form. So the same idea, you understand? The same idea can be extended to the solution of Silverstone equation as well. So here it goes, then you can see. So here is the same thing. So here A is smaller than B. So we reduce the matrix A transpose to the real suit. And B matrix is transformed to a Heisenberg matrix. So that's what I said. So A transpose is transformed to real suit matrix R, and B matrix is transformed to the Heisenberg matrix H. Okay, U and V are two transforming matrices. They are orthogonal matrices. So if you do that, then as I showed for the Lyapunov matrix equation, the same way we can show that the matrix XA, the matrix equation XA plus BX equal to C becomes YR transpose plus 8YWC C hat, where C hat is V transpose CU and Y is V transpose XU. Remember in the other case, Y was U transpose XU, but since there are two matrices involved here, one U transform one matrix, the V transform the other matrix. So Y has to be related to U and V both, right? You can do the simple calculation to see that this will happen. So now the problem will be how to solve this matrix equation. YR transpose plus 8Y equal to C prime by taking advantage of the structure of the matrix H and R. Okay, R is real suit matrix and H is a Heisenberg matrix. So again, the same type of thing. So we don't do anything with the Heisenberg matrix. We just work on the real suit form. If the k minus 1th entry of the real suit matrix is 0, then we can compute the corresponding column yk by solving a Heisenberg system. Remember, in the other case, the yk was solved by using a triangular system because R was a positive triangular system. But here, the system is a Heisenberg system. And again, Heisenberg system also can be solved in order n square operations. So it's not an expensive process. Because you apply Gaussian elimination to Heisenberg matrix. Heisenberg matrix is almost triangular, which has just one extra diagonal. So the work to be done is much less than in the matrix A and matrix squared full matrix. So instead of Gaussian elimination applied to a full matrix needs about n cube over, I think 2n cube over 3 operations. But Heisenberg system requires only order n squared operations. Anyway, so this operation is quite simple. And then the other case, case 2, when the subdiagonal entry, the RK k minus 1 is different from 0, then we can compute yk and yk minus 1 again by solving solving two systems of linear equations, each system involving a Heisenberg matrix. That's it. So it's an immediate generalization of the Schur algorithm for the Lyapunov matrix equation. So since the Lyapunov matrix equation is solved transforming the matrix A to a real Sur matrix is called the algorithm is called Sur algorithm. And here XA plus BX equals C is solved by transforming A transpose to real Sur form and B to the Heisenberg form. The algorithm is called Heisenberg-Sur algorithm. And of course, once you have the solution matrix Y, then you can recover X as dy. That's it. Okay. And this is the standard algorithm now to solve the Silber's matrix equation. And you can now see that the Sur algorithm for the Lyapunov matrix equation is just a special case, right? Just a special case. So let's look into an example. Suppose A is 2 by 2, B is 3 by 3, and C is of course 3 by 2 then. Now square matrix. So if you reduce the matrix A transpose to real Sur form and B to Heisenberg form, so R happens to be in this case is 2 by 2 diagonal matrix. Very simple. It just turns up, it happens that way. And H is Heisenberg matrix. You can see H is Heisenberg matrix, right? And this Heisenberg matrix is unreduced because both the subdual and integer become complete. And C hat looks like this. We just go C. So since So in this case, there are no 2 by 2 blocks. So that's a good news. So all you have to do, we compute y2 and y1 just by solving a Heisenberg system. There are no 2 by 2 blocks. Okay. It just happened. Okay. So we solve first, we compute y2 and then y2 by solving this Heisenberg system. Then once y2 is computed, then you can compute y1 by solving another Heisenberg system, and you are done. Because y has only 2 columns here, y1 and y2. And once y is computed, then you can recover x from y by multiplying y to the by b to the left and b transpose to the right. That's it. Now, that was a simple case, but here is a little more complex case here. I mean, a little more. But here the Heisenberg matrix, I mean, say real Sur matrix is not a triangular matrix, but it's at a 2 by 2 diagonal block. So in that case, the y3 has been computed by solving Heisenberg system. And once y3 is computed, then we can compute y1 and y2 simultaneously by solving 2 systems equation, 2 systems of Heisenberg equation. Okay, so let's see how it goes.
So does it happen practically order of B is greater than order of A in this case? In this case, you have shown order of B is greater than order of A. But does it practically happen?
Yeah, if you have to choose if there are 2 matrices. So you apply you transform the lower order matrix to real Sur form, and the upper order the higher order to
Heisenberg.
So you call order. You can call this is A, this is B, depending on. So here that's why I say y3 now. Remember there is R3 equal to R32 equal to 0. So y3 is computed just by solving one Heisenberg system. And then y1 and y2 are computed by solving 2 Heisenberg systems. Okay. and you get y, and then multiply v y transpose, you get. So, the thing is to just practice at home. See, do this, do all the steps one by one, then you will see how it goes. Okay? You have to do it at home. While using MATLAB, you can do that. Now, MATLAB has a command, liap. Liap solves both Sylvester's equation and the Lyapunov matrix equation. We use that command in the tutorial class. We'll see how it goes. Yeah, MATLAB command x equal to liap ABC. Solve the Sylvester equation x plus x equal to c. And if there is no base, just x equal to liap AC. Solve the Lyapunov matrix in the form, remember, not in the form x plus a transpose equal to c, but in the form ax plus x transpose equal to c. So you have to always remember that. MATLAB does little differently than what it did in this class. We are trying to solve the equation x plus a transpose equal to c. But MATLAB says ax plus x transpose equal to c. Okay. So that means you have to input a transpose instead of x. That's all. But for ax plus x equal to c, I don't know, did I do x plus bx equal to c or ax plus x equal to c? I thought I did x plus bx.
X plus b.
So again, you have to do the, you have to check. You have to change the order and these. So this MATLAB solves ax plus x equal to c. So when you input a, b, and c, you have to do that in that order. Okay. So if you solve xa plus bx equal to c, so your b and a have to get interchanged. To use the MATLAB command. But the one thing I'm not going to talk about here is the following, but just for your information, those of you who are advanced students, they might look into my book. The thing is that in many practical applications, we don't need the full solution matrix. Suppose you are solving the Lyapunov matrix sequence xa plus xa transpose equal to c. We don't need the matrix X, complete matrix X. All we need sometimes assuming that X is symmetric, positive, definite. Many applications we need just the Cholesky factor. Remember, any symmetric, positive, definite matrix X can be factorized into Cholesky factorization, LL transpose. Remember, in many practical applications, all you need L or L transpose. So you can apply the whole process, then decompose the solution matrix X into LL transpose, get the matrix L. That would be wastage of time. Right? So there is an algorithm. There's an algorithm to directly obtain the matrix L without going through the whole operation. So if you are interested, you can look into the book. But it's something just I did not care. Rajiv, can you help me now?
Yeah. Different chapter.
Okay, do you remember the algebraic Riccati equation that we talked about yesterday? So here is the continuous time algebraic Riccati equation called KR. So KR looks like this. XA plus A transpose X minus XB R inverse B transpose X equal to Q or something like that. Q, right? Q. Because this Riccati equation comes from, remember, comes from the arises in the solution of optimal control problem. Okay. The problem where you have to minimize a quadratic function, remember, and such that A minus BK will be stable, remember, and the matrix K is formed out of the solution of this Riccati equation. So that's why Riccati equation is important to solve. You remember the whole thing, right? Okay. Now, since it is a quadratic equation, it's not a linear equation any longer. So we'll not be able just to solve this equation just by transforming the matrix A to real Schur form or to Heisenberg form. That's not possible because it's not a linear equation any longer. You understand the problem? So in that case, we have to do something else. What is the something else? Now, associated with this Riccati equation, we can define a 2n by 2n matrix called the Hamiltonian matrix, where this, the S here is just in, B, S is B R inverse B transpose. So the Riccati equation here is XA plus A transpose X minus X S X. That's the Riccati equation. So associated with this Riccati equation, we can define a 2n by 2n matrix, which has a very special structure, which looks like that, diagonal blocks are A and minus A transpose. Okay. And the off diagonal blocks are minus S minus Q. So this 2n by 2n matrix is called the Hamiltonian matrix. Okay. Now, what does this Hamiltonian matrix have to do with the Riccati equation? That's the question. Okay. The answer is the following. A matrix X is a solution of the KR if and only if the columns of the matrix IX span an n-dimensional invariant subspace of the Hamiltonian matrix A. So problem A, many of you are not familiar with this concept of invariant subspace. It's a subspace associated with the eigenvectors. Okay, but let's not bother about that. We can just bypass it. Let's see. Here is the most important result for you. So, remember in the context of solving optimal control problem, right? We need to find a stabilizing solution X, symmetric positive definite stabilizing solution. Stabilizing solution X means that the solution X that is used to form the feedback matrix K, which will be stable. Which will make the system stable. Okay. So stabilizing solution X means the solution X which is used to form the matrix K, which stabilizes this system. That's what stabilizing solution means. Okay. So it says the following, that this matrix equation has a symmetric positive semi-definite stabilizing solution X if and only if the matrix AB is stabilizable and the associated Hamiltonian matrix has no pure imaginary eigenvalues. Okay, so that is a theoretical, very nice theorem that relates the solution of the Riccati equation with the Hamiltonian matrix. So that means our purpose will be to work with the Hamiltonian matrix now, try to find an invariant subspace associated with the stable eigenvalues only. Because we don't want the imaginary eigenvalues, right? Because say the matrix H cannot have any imaginary eigenvalue. If the matrix H has any imaginary eigenvalue, then that solution will not be stabilizable. Okay. So we have to work with the Hamiltonian matrix in such a way that we can filter out the imaginary eigenvalues so that the solution will be a stabilizing solution. So let's see, it's kind of hard for me to explain the details, but let's see how we can do that. Let's see the algorithmic how we can do that. So here, instead of finding the real suit form of the matrix A, we'll find the real suit form of the Hamiltonian matrix. You see the theorem that says how to express the solution X of the Descartes equation in terms of the invariant subspace associated with the Hamiltonian matrix. Invariant subspace of the Hamiltonian matrix associated with the eigenvalues which are stable. Okay. So the idea is mathematically, I'm showing you the computational algorithm. Mathematically, the idea is to construct an invariant subspace of the Hamiltonian matrix associated with the eigenvalues which are stable. That's the mathematical idea. Okay, if you don't understand it very well, so just you can ignore it for the time being. Let me show you the algorithm how to do that. Okay, maybe you can jump somewhere. Can you help me? Jump, you will be solution. Okay, before I talk about this algorithm, I have to make one more remark. When we compute the real suit from a matrix A, we get the eigenvalues in matrix A anyway. But they might appear in any order. Okay. If you want the eigenvalues to appear in a certain order, for example, suppose I want all the eigenvalues in matrix A with real part negatives first, and then the other eigenvalues. We have to do some more work. Okay. And then by doing that, we can arrive a form called ordered suit form. because order means that it orders the eigenvalues of the matrix. Okay, and there is a MATLAB command to do that too. Okay, to find the order suit form. But for most practical purposes, you don't need that. But thing is for solving the Riccati equation, you need that. You need to have the eigenvalues of the Hamiltonian matrix appear in certain order. Actually, as I said, we are trying to construct the invariant subspace associated with the stable eigenvalues. That means we want the stable eigenvalues to appear first, and then the non-stable eigenvalues. Okay, and we'll make some assumptions so that there will be no imaginary eigenvalues, because we have to filter that out. Remember that the theorem says. So that's what we're going to do. So the assumption is, as I said yesterday, AB should be stabilizable and AQ should be detectable. The first step is form this Hamiltonian matrix. Actually, this you can call it AS equal 1. So A minus S minus Q minus A transpose. So form this Hamiltonian matrix. From the equation of the from the Riccati equation. Okay, and then you transform this H to order real suit form. That's what I'm saying. Order real suit form. Or you order the eigenvalues in such a way that the eigenvalues of the H with negative real parts were all contained in the first subdiagonal block. I'm sorry, first diagonal block. Okay, you see that the order real suit form can be written in this form, where T11, the subdiagonal block, diagonal block T11 will contain the eigenvalues with negative real parts only. And T22 will contain the eigenvalues with positive real parts. And the assumptions that we made, that will guarantee that there will be no imaginary eigenvalues. Okay. You hear what I'm saying? So once you have this,
Equal.
Huh?
It's equal. Your sound.
equal. Okay.
But it should only consist of stable eigenvalues.
Yes. Because we remember our purpose is to construct the invariant subspace associated with the stable eigenvalues only, to get the stabilizing solution. Okay.
But here T22 you said it is.
C22 will not be used for our purpose. But we have to have the real suit from order in such a way that the first diagonal block will contain only the eigenvalues with negative real parts, the stable eigenvalues. Okay. So actually there are 2n eigenvalues here, because H is order 2n, right? So n eigenvalues have positive real parts and n have negative real parts. So negative real eigenvalues will appear, appear in the block T11. Okay. And once you have this real suit decomposition of the matrix H in this ordered form, then what you do, you partition the matrix U conformably. That means your U11 corresponds to T11. Okay. Remember, your real suit form is of the order U transpose HU is this block diagonal matrix. Okay. And matrix U is orthogonal. So you can partition now U in the same way as the blocks in T appear. So that means U is U11, U12, U21, U22, where U11 corresponds to the matrix T11. And U21 is corresponds to the zero part. So once you have that, then your solution matrix X will be given by solution of the linear systems equation X U11 equal to U21. It's a linear system because U11 known to you, U21, I'm sorry, U21 is known to you, and you have to find U11. That's it. I mean, you have to find X. Okay, U11 known, U21 known, you have to find X. Okay, it's a system of linear equations to solve. In theory, X is nothing but U11 inverse U21, but you don't want to do that in a computational setting. In theory, it means X equal to U11 inverse, I'm sorry, U21 times U11 inverse. You don't want to invert matrix U11, so you want to solve this. Yes, that's it. So it can be shown that if you do this, X is the stabilizing solution, and X is the stabilizing solution of the Riccati equation. And from this stabilizing solution, you can form the matrix K such that A minus BK will be stable, and the quadratic function appearing in optimal control problem will be minimized. Okay. That is, as I said, there is software to do that, software for ordering the real suit from the matrix A. You can look into MATLAB. And here is an example. If you want to follow this, if you follow the algorithm, you can do it. This is a simple example to follow. So your H matrix is 2n by 2n matrix of this. Q is an identity matrix, and R is just 1 in this case. So your H matrix looks like this. So transform this H matrix into order real suit form. Here is your matrix T11, here is your matrix T22, here is something else. You look here. And then U11 and U21, you have to remember you need the real suit form and the transforming matrix in both. Okay. From U, you have U11, U12, U21, U22. Okay, for our purpose, we need just U11 and U21. We don't need U12 or U22. So you have this is your U11. Remember, it's a H is a 6 by 6 matrix. Okay, so each block is order 3. So U11 is order 3, U21 is order 3, and once you have it, you just plug in X equal to. I just computed it explicitly, but you don't do that in practice. So this is your X matrix, and you can easily see that the matrix A minus Sx is stable. Okay. So X is the stabilizing solution. And there is an algorithm called the mat control function called RIC SCHC. So Riccati equation for continuous time Riccati equation using suit form. Okay. And MATLAB has a command called care. The same thing. It also solves the Riccati equation, continuous time Riccati equation. For the discrete time, there's another Riccati equation. Is MATLAB has a command called there. Okay, we'll stop here today and come back in the afternoon. I think.
Will it be continuous now? You are discussing about
Yes,
So 3 to 5 will be a lecture on port placement and associated algorithms.